Hello, my name is Chris, and I am joined today by Cyan, Isabel, and Victoria to share our research on solar cells and how they connect to the field of quantum chemistry.
The topics we will be discussing today are Introduction to Solar Cells, how solar cells related to quantum, the evolution of solar cell technology, and future directions.
So, what are the solar cells? The photovoltaic PV cells, or as we commonly call them, solar cells, are non mechanical devices that convert sunlight into electricity, or in some cases, convert artificial light into electricity. Solar cells can be arranged into arrays, which are composed of thousands of individual cells that can function as a power station for commercial, industrial, or residential use through the conversion of sunlight to electricity. Solar cells are also composed of semiconductor material, meaning they will conduct electricity better than insulators, but not as well as conductors like metal. There are multiple materials used as a semiconductors, but silicon is by far the most common semiconductor material used in solar cells, representing approximately 95% of the modules sold today. It is also second most abundant material on Earth after oxygen and most common semiconductor used in computer chips. Crystalline silicon cells are made of silicon atoms connected to another form of crystal lattice. This lattice provides an organized structure that makes conversion of light into electricity more efficient. Solar cells made out of silicon currently provide a combination of high efficiency, low cost, and long lifetime. Modules are expected to last for 25 years or more, still producing more than 80% of their original power after this time. When the semiconductor is exposed to light, it absorbs the light energy and transfers it to the electrons. This extra energy allows the electrons to flow through the material as an electrical current. This current is extracted through the conductive metal contacts and can be used as a power source. The amount of electricity produced from the cells depends on the characteristics like intensity and wavelength of the light available and multiple performance attributes of the cell. An important property of the solar cell semiconductors is a band gap, which indicates what wavelengths of light the material can absorb and convert to electrical energy. If the semiconductor's band gap matches the wavelength of the light shining on the cell, then that cell can efficiently make use of all the available energy. The electron's movement towards the front of the surface of the solar cells forms an imbalance of the electrical charge between the front and back surface of that cell. Due to that imbalance, the voltage potential is created, similar to the battery's positive and negative terminals. On the cell, electrical conductors absorb the electrons, and through the connection to an external load in an electrical circuit, allow the electricity to flow through that circuit.
The functions and processes of solar cells are actually closely related to quantum chemistry due to the fact that it directly works upon the quantum mechanical principle of the photoelectric effect. This occurs when electrons are ejected upon the impact of electromagnetic radiation, a category that light energy falls into, onto specific materials, which are often composed solely of metal. These electrons and their unique nature of solely interacting with electromagnetic radiation allows them to be identified as photoelectrons, also commonly known as photons. These electrons and their identification as photoelectrons or photons demonstrates wave-particle duality, which states that light can exist as both a discrete quanta of energy or electromagnetic radiation, which comes as waves. The double slot experiment is a good demonstration of this wave-particle duality. With these combined information, Einstein crafted a formula that summarizes the photoelectric effect and, in turn, the work of solar cells. Based on the given equation, it can be surmised that the number of ejected photoelectrons depend on the metal surface being used, specifically its crystalline structure. Photovoltaic cells typically utilize thin film semiconductor materials such as amorphous silicon. In turn, this allows photons to form in arrays that enable high electrical energy output.
We started with traditional bulk semiconductor cells harnessing sunlight to generate electricity. Now we enter the era of innovation with quantum dots. These tiny nanoscale wonders revolutionize solar cells, offering unprecedented efficiency. Quantum dots, with their size dependent electronic properties, bring a quantum leap into the energy absorption field. But what sets them apart is the manipulation of their band sizes. Quantum dots allow precise tuning of energy levels, optimizing the absorption of different wavelengths. This not only boosts overall efficiency, as we'll see later, but also opens the door to a broader spectrum of energy solar capture. The figure on the right demonstrates this. As the bulk semiconductor material gets turned into quantum dots of different sizes, the energy band gaps also change. Alongside those, the energy levels move from continuous to discrete. There are a few factors that come into play, one of which we already discussed previously. The ability to fine-tune band gaps to access new wavelengths of light would be a profound breakthrough for solar technology and would help increase cell efficiency. In addition, the cost and ease of production play pivotal roles in this transition. Quantum dot technology introduces scalability, simplifying the manufacturing process. This is not only going to reduce production costs, but it also makes clean energy more accessible on a larger scale. Furthermore, the reduced form factor of quantum dot solar cells is a game changer. These miniature powerhouses offer increased flexibility and integration, fitting seamlessly into various surfaces, from buildings to portable devices. On the left, we can see a variety of ways in which we can easily produce these quantum dot solar cells, such as molecular linkage, electrophoretic deposition, chemical baths, and spin coating, which is shown in the upper diagram. Traditional solar cells, while reliable, face limits defined by the Shockley-Queisser theory. The maximum theoretical efficiency hovers around 31%. This constraint stems from the inability to harness low-energy photons and through the loss of excess heat as energy. Quantum dots disrupt this efficiency landscape. With their unique size-dependent properties, quantum dots redefine the game. Theoretically, they can overcome the Shockley-Queisser limit, capturing a more extensive range of photons and minimizing energy loss. This allows their theoretical efficiency to skyrocket to a surprising 66%. Although current prototypes of these quantum dot solar cells only reach efficiencies up to 4.4%, there is promise in this technology, and research is being done to improve upon these efficiencies.
Due to the recent advances in research and development, the production of advanced photovoltaic devices will continue to grow. In 2022, global PV power capacity grew by 239 gigawatts and reached almost 1,200 gigawatts, equating to 1.2 terawatts. The vision of photovoltaics is to be used in everything, everywhere, including in electrical power, transportation, heating, and the generation of fuels. However, challenges have arisen, such as cost, and although solar technology has been cheaper than ever, it is still considered high in installation and maintenance. Additionally, material availability and supply chain also pose a challenge. Weather conditions pose a threat to PV, as cloudy or rainy days reduce the amount of energy produced by solar panels. As well, these solar panels can only generate electricity during the day and need to store power to be used at night, and storage batteries can increase cost. Lastly, government incentives favor traditional fossil fuel sources, making transitioning into solar cell energy more difficult. Researchers have been planning future research to work around these challenges before commercializing next generation device designs. One direction that has been proposed is for the devices to be coupled, meaning coupling two or more materials to create low cost atom devices. Another proposition has been coupling PV with other energy sectors in the clean energy economy. Additionally, solar technology is also being integrated into our everyday lives, such as solar powered chargers for phones and laptops, as well as clothing and backpacks with built in solar panels. Scientists are also emerging PV technologies, including perovskites, which are solar cells that have a high conversion efficiency, over 25%, and low production cost. Bifacial PV modules are also included in the emerging PV technologies, as they can collect light on both sides of the PV cells. Lastly, concentrator PV technology utilizes low-cost optics to concentrate light onto a smaller solar cell. I also provided a table that displays the recent solar projects in the US that are anticipated to commence construction in 2024. Even the smallest advances in reliability, manufacturing, efficiency, and innovation design will have a major impact on the future of solar cells.
Thank you so much for watching.